Okay, so still 117.17. So molecular geometry, and this is kind of similar. The arrangement of atoms in a molecule determines their characteristics. And this is kind of the thing I was saying about the arrangement of atoms in a metal determines, that causes them to be malleable and ductile and good conductors. We talked a little bit about molecular polarity, and that's uneven distribution on charge in a molecule. So an atom a molecule that has molecular polarity is a polar molecule. Name me a polar molecule that we've talked about. M-I-C-K-E-Y. H2O, yeah. I need to find a way to make that hydrogen dihydrogen monoxide. Yeah, it doesn't really work. So we haven't always known the shape of molecules. And did anybody here watch Secret of Photo 51 in biology? It's about Rosalind Franklin and the race to find the shape of the DNA molecule. How do you figure out the shape of a molecule? It took decades with DNA of different people coming at it from different angles. You do testing. You actually fire things like X-rays at the molecule. You make models. That's what Watson and Crick did. And you have to, once we understood more about how the electrons behaved, once we had quantum model of the atom, you also have to figure out how those electrons are behaving to shape a molecule. So that is molecular geometry. It's the shape of molecules. Notice that this is not ionic or metallic geometry. Here we're dealing all with molecular substances. Ionic geometry we really handle more when we talk about crystalline solids. And when we go to the museum in the spring, we'll do a little preliminary unit on basically what works out to be ionic geometry. It's the geometry of crystal formation. But I imagine now that we're doing the crystal growing thing, we're going to dip into that a little bit prior to that point. Okay, so molecular geometry. Well, how things are shaped. There's a rhyme and a reason. And the theory, the body of evidence that sums up, or the body of thought that sums up the reasons behind why things are shaped the way they are, is what's called VSEPR theory. It's not a direct pronunciation, obviously. We're butchering that, VSEPR. But it's valence shell electron pair repulsion. And what it means is that electrons want to be as far from other electrons as possible, because they have like charges. So you have, within an orbital, you've got two electrons, and they're okay with that for reasons of subatomic physics that I don't fully understand because I'm not a particle physicist. But one little orbital full of electrons is fine. The other part of it is that the nuclei of two things that are attached want to be as far away from one another as possible. So those little positive cores also want to be as far apart as possible. So if I have three things, and we'll kind of have to imagine that, here's one thing. If I have three things that are all hooked together, the farthest apart they can be is in a straight line. Because that gets all the little electrons that are circling them as far apart as possible. That gets all the nuclei as far apart as possible. And so whatever form will get things as far apart as possible is the form they'll take. So what does this mean? It means that if you only have two or three things, they line up in a straight line. This is called a linear arrangement. Linear because it's a line. It's not all that creative. A molecule that has three atoms will also be linear, as long as there's nothing else on that central atom. Something that's got four things hooked together assumes what we call a trigonal planar geometry. I'm going to show you what that looks like. In a trigonal planar molecule, this makes a triangle. Okay, duh, trigonal. but they're all in a flat plane. If you look at it flat on, these things are in one single plane. It's basically two-dimensional. They're not pushed up or down because these are the only three things on that central atom. And the central atom in molecular geometry really is what controls the geometry. That's an important point. So the central atom largely controls geometry. So typically when we're looking at geometry, we're asking how many things are hooked to the central atom. That's sort of the first question we tend to ask. Now, if we have 5 things, so a central atom with 4 things connected to it, what we get is what we call a tetrahedral arrangement. I'm going to tell you in a second. So this is a tetrahedral molecule. No matter how it lands, one side is up. You can sit and play with it all day. There's always one point up. It's kind of like it's like jacks but worse. Jacks are the bane of all parents because kids leave them on the floor and then you walk across the living room barefoot in the middle of the night to let the dog out and you step on them and you scream words that will wake your 4-year-old up, guaranteed. So, no matter how you toss this thing, it will land with a point up. Caltrops were an anti-cavalry weapon used in the Middle Ages. And a caltrop is, in essence, 2 sharpened pieces of wire joined together by heat so that no matter how you toss it, one point lands up. So if you scatter caltrops in front of an approaching cavalry, guess what happens? Their horses are all lamed. And the cavalry is not marching anymore. They can also be used as an anti-vehicle with pneumatic tires kind of weapon. I think in some James Bond somewhere there's a bucket of caltrops that gets released from the back of a vehicle, flattening the tires of everybody who comes behind. That's a tetrahedral arrangement. And what's governing that tetrahedral arrangement is that everything is trying to push as far apart from everything else as possible. Now, the interesting thing is this. Okay, so let's make water. You've drawn water, right? What's water comprised of? 2 hydrogen, 1 oxygen. What's in the middle? Oxygen. I'll put those nice big, oh, those aren't very juicy. That's nice juicy, those aren't much better. Electrons there, and we'll put our little hydrogens out here, and the hydrogens, of course, only have 1 to share. So they move right in, and it's like doing a puzzle. Oops. Ah. And they just plug in like that. So is water a linear molecule then? Sure looks like it, but the tone of my voice tells some of you that there must be a trick. She wouldn't sound like that if this was easy or straightforward. So, what's the central atom here? It's the oxygen. Remember that the central atom is the big thing that governs the geometry. And this central atom has some, how many things are attached to this central atom? 2 other atoms. Is there anything else attached to this central atom? 2 what? 2 unshared pairs of electrons, you said? You thought? But you didn't want to say anything because you're too shy and it's a Tuesday/Monday. You had a long weekend. There are 2 unshared pairs attached to this thing. Now, here's the deal. These guys want to stay as far apart from one another as possible. So do these. So in fact, there are 4 things attached to this central atom. Only 2 of them look visible to us, which are those other atoms. But those unshared pairs act just as if they were other atoms. So water, in fact, looks like this. Whoa! When we draw water in a Lewis structure to represent this, we draw it, it's called a bent molecule. And what that shows is that those hydrogen get pushed down because the little electrons are repelling the valence shell, whatever electron cloud is still around the hydrogens. Even though it's not much, because water is pretty electronegative, it tends to suck most of the blankets off the hydrogen. It pulls a lot of it. So the angle is smaller than we might expect otherwise. But they get sort of deformed. They get shoved down until they're held like this. In the model building kits, these little Mickey Mouse ears are actually paddles that represent unshared electron pairs. So these represent an orbital with 2 electrons in it. So this is not a linear molecule, even though it, when you look at it and you go, oh, H2O, 3 things, it should be. This is a bent molecule, and it's an important distinction. Now, all that aside, these are 2-dimensional drawings. You can't represent everything that's 3-dimensionally true about them, but we try our best. So there's a system that we use. What we just talked about, that when you have unshared electrons, I guess this is the slide I added in response to what I felt was some lack of clarity. The unshared pair repels the other stuff just like another atom would. So stuff that has unshared pairs on the central atom, it doesn't matter if there are unshared pairs on the things that are attached to the central. Unshared pairs, I should clarify that, on the central atom. Whoops. Things that have unshared pairs on the central atom will tend to have different geometries than we would expect. And really, what is water? Well, it's tetrahedral. It's the same geometry as this. It just happens that 2 of the things you can't see. They're kind of invisible. So when we're looking at geometry, and this is not something that's in your notes, this is something that I want to talk about that kind of falls outside what's on your slides. When we're doing the molecular geometry lab, it's going to become really important. There's a way to predict geometry based on how much stuff is hooked to the central atom. So if you'd be so kind as to go to page 186 in Holt Modern Chemistry. Okay, so you've got the lab packet here, and what you're going to do for each molecule listed is you're going to construct it, you're going to draw it as a Lewis diagram, and you're going to list its geometry. So if you, actually, weirdly enough, I'm going to ask you to flip to the back page first. And we'll actually walk through this for water together. It's the 3rd one down, it's H2O. So what they want to know first is the number of lone pairs on the central atom. Those are unshared pairs. So for doing water, number of unshared pairs, how many is that? 2. You got 2 unshared pairs. Don't start that. And you're only worried, this is important, you're only worried about the unshared pairs on the central. So that would be 2 for water. Total number of effective pairs around the central atom. And for that, the number of effective pairs are the total number of atoms that are hooked to that central atom. So for water, that's also 2 for H2O. Let me move that over. And I'll show you an example where that's different than the number of bonds. In this case, there are also just 2 bonds. Gesundheit. And there are 2 things. So here's where the formula comes in. The arrangement of electrons based on the number of effective pairs. Everything is A something, B something, E something. So A is your central atom. A is always going to be 1. There's not going to be a subscript in any of the ones that we're dealing with because we're not dealing with things that have more than 1 central atom. So that's easy. B relates to the number of effective pairs. So the subscript here is going to be the number of things that are tied to the central atom, the number of atoms that are tied to it. So far we have an AB2. And the subscript for E is going to be the number of effective pairs. So that's going to be AB2, E2, though I didn't write my 2 very well. That code, that ABE code, is going to tell you what your geometry is. So if you look at this table, you can look here and go, oh, well, AB2, and they only give an AB2E. But AB2E2 is going to function just like something that has 4 things hooked to the central. So it's going to be, in essence, it's going to, the arrangement will look tetrahedral, though we can't see 2 of those things. And that's kind of where we talked about this thing looks bent. Now, not every eventuality is covered on this table, but most of them are. And some of these you're actually going to be able to get directly from the table. When we talk about the bonds, the angle of the bonds around the central atom, let me shrink all of this. You're actually going to construct this. You're going to get a protractor out, and you are literally going to measure this angle on your constructed model. Now, you can then compare it to the chart, but I want to see the actual measurement that you got with your constructed thing. The geometry of the molecule, the shape, is going to come from that table. So the shapes that we're going to list are linear, bent, angular, trigonal planar, tetrahedral, trigonal bipyramidal. Oh, there it is, AB2E2. Bent or angular, trigonal, bipyramidal, and octahedral. So you're going to list those shapes. Okay? You want to get started? Okay. You'll go to your lab tables. This is kind of, it's stinky working conditions because we don't have lab stools still. So I guess I'll give you the option. You can either go to your lab stools and stand around the lab stools or lab tables, or you can work, you can move into your lab groups here at your desks and work at the tables. You will need a model kit. You're going to find those over there by the hot plates. You will need a protractor. You'll find those over there in the cubby of things. Oh, let me say one more thing. One more thing. For the first, what is it? The first 8, 2, 4, 6, 8. First 10 conform to the Gooch math. Here's what I don't want. Here's what I want you to do. I want you to go through the process of building it, drawing the Lewis structure, and then doing the data table on the back. So for one molecule, build it, Lewis structure it, do the data table, then go to the next one. Build it, do the Lewis structure, do the data table. Or Lewis structure and build don't have to be in the same order. For every single one you build, take a picture of your model next to your Lewis structure, because you're going to turn those in. You're going to create a document, each of you. So everybody should take a picture on their iPad, and each of you, I will create a submission slot. Each of you will actually submit a picture of your model with your Lewis structure next to it. So we're going to be we're probably going to be working on this for the next 3 days, interspersed with some lecture that relates to it, just 10 or 15 minutes here and there. Okay, grab your kit, grab your protractors, get going. I'm going to float around.